Hello, explorers, and welcome back to a journey that will absolutely shatter your perception of reality. Today, we are diving deep into one of the most mind-bending ideas in all of physics, the incredible secret of light. Imagine looking up at the night sky, seeing the faint twinkle of a star that is millions of light years away. For all that time, for what feels like an eternity, a tiny particle of light has been on an epic voyage across the absolute emptiness of space. It crosses an unimaginable distance just to end its journey by landing perfectly in your eye. Now, what if I told you that for that very particle of light, its incredible journey took no time at all? That from its perspective, the moment it was born in that distant star and the moment it arrived in your eye happened at the exact same instant. And even stranger, that the millions of light years of distance it crossed was for it precisely 0. This sounds utterly impossible, does it not? A journey of millions of years cannot be instant. A distance of trillions of miles cannot be 0. It feels like this violates every basic rule of our everyday reality. Yet this bizarre conclusion is a direct and unavoidable consequence of one of the deepest truths about our universe. It is a rule so powerful that space and time themselves will literally stretch and shrink and warp to make sure that this rule is never, ever broken. To truly grasp this, we have to stop seeing the universe from our human perspective and try to imagine it from the viewpoint of light itself. And what we will find is one of the most profound ideas in all of physics, that for light there is no space and there is no time. Before we can completely break the rules of reality, we first need to understand the rules we think we live by. Our entire lives are built on what feels like an obvious, undeniable truth about space and time. Imagine you are just standing in your room and you decide to walk to the other side. You know without even thinking about it that this simple action will take some amount of time, maybe a few seconds. You also know that you have to cover a certain distance, perhaps a few meters. This relationship is simple and wonderfully predictable. Speed, as we all learned in school, is simply distance divided by time. This intuitive and comforting view of the world was formalized centuries ago by the brilliant Sir Isaac Newton. For him, space was an absolute unmoving and unchanging stage where everything happened. A meter was always a meter, no matter where you measured it. Time was a universal clock ticking away at the exact same rate for everyone and everything across the cosmos. It flowed like a great constant river, carrying all of us along with it at the same pace. This is the world of classical physics, and for just about everything in our daily lives, it works perfectly, beautifully fine. Let us think of a classic example. If you are comfortably seated on a train moving at a brisk 100 kilometers per hour, and you decide to throw a ball forward inside the train at 20 kilometers per hour, relative to you, what happens? Someone standing still on the platform outside will see that ball zipping by at a combined speed of 120 kilometers per hour. The speeds just add up. It is common sense, right? For centuries, every brilliant mind assumed this simple addition worked for everything in the universe, including the fastest thing we knew, the speed of light. The thinking was logical. If you were on a spaceship moving super fast, perhaps at half the speed of light, and you then turned on a flashlight, that beam of light would travel at its normal speed plus the speed of your ship. It seemed utterly obvious. It seemed impeccably logical. And it was, in fact, completely wrong. This simple, stubborn fact, the constant speed of light, would eventually force a complete demolition and rebuilding of our fundamental understanding of space and time. The crack in the foundation of our understanding actually appeared in the late 19th century, when physicists were grappling with James Clerk Maxwell's brilliant new theory of electromagnetism. Buried deep within his elegant equations was a truly startling prediction. The speed of light in a vacuum represented by the letter c was a constant. It did not matter how fast the source of the light was moving or how fast you, the observer, were moving. It was always the exact same number, about 299,792 kilometers per second. This was utterly baffling. How could the speed of light be the same for someone who is standing still and for someone who is frantically chasing after it at half its speed? It directly violated the simple common sense logic of our train and ball example. How could that be? This is where a young, unassuming patent clerk in Switzerland stepped onto the stage of physics and changed everything. His name was Albert Einstein. In 1905, a year that would forever be known as his miracle year, Albert Einstein published his groundbreaking theory of special relativity. It was built on just two ideas or postulates that sound deceptively simple, almost harmless. The first one is called the principle of relativity. It simply states that the laws of physics are the same for everyone in uniform motion. Now, this is basically just an extension of our intuition. Think about it. If you were on a perfectly smooth train with no windows, you could not do any experiment like throwing a ball or pouring a liquid that would prove that you were moving. The laws of physics work the same within your moving frame of reference. Only your motion relative to someone else matters. The second postulate was the real bombshell. Einstein bravely took Maxwell's weird counterintuitive result and ran with it, declaring it a fundamental truth of the universe. He stated that the speed of light in a vacuum is the same for all observers, no matter how they are moving or how the light source is moving. Let that sink in for a moment. This means that if a rocket flies past you at an astonishing 99% the speed of light, and the pilot turns on a laser, both you on the ground and the pilot inside the rocket will measure that light beam traveling at the exact same speed. The cosmic speed limit, the speed of light, is absolute. This is the precise point where our common sense completely shatters into a million pieces. To accept both these incredibly simple yet profound ideas, something fundamental has to give. If speed, which we know is distance divided by time, is an absolute constant for light, then the distance and times themselves cannot be absolute. They have to be relative. They have to stretch and shrink depending on your motion. This was Einstein's revolutionary, audacious leap of genius. He realized that the universe does not have a master clock ticking universally for everyone, nor does it have a master ruler measuring absolute distances. Instead, it has a universal speed limit, the speed of light. And the very fabric of space and time will warp and distort in truly bizarre ways to make absolutely sure that no one ever breaks it. What we experience as separate entities, space and time, are actually woven together into a single inseparable thing, space-time. And this incredible fabric of space-time gets distorted by motion. To truly wrap our heads around just how incredibly weird and wonderful this is, we need to employ one of physics' most powerful tools, the thought experiment. Imagine a clock. But not just any clock. This is a special light clock, the simplest one you can possibly imagine. It is just two mirrors facing each other with a single particle of light, a photon, bouncing perfectly between them. Every time the photon hits the bottom mirror, we count it as one tick. Simple enough, right? Now let us put this light clock on a table right in front of you. You watch the photon travel up to the top mirror and then bounce back down. Tick up, down, tick. The distance between the mirrors is fixed. The speed of light is constant. So the time for each tick is perfectly regular, predictable, and comforting. This is your clock at rest. But now, let us put that exact same light clock on a transparent spaceship and watch it fly past you at, say, a super speedy 80% the speed of light. For the astronaut inside that spaceship, absolutely nothing has changed. According to Einstein's first postulate, the laws of physics are the same for her. She sees the photon going straight up and down, just like you did when the clock was at rest. Her clock appears to be working normally. But what do you, the person standing on the ground, actually see as the ship zooms by? You do not see the photon going straight up and down. Why? Because the entire clock mirrors, and all is moving sideways as the photon travels. So, from your perspective, you see the photon travel along a diagonal path. It has to travel up at an angle to hit the moving top mirror, and then back down at an angle to hit the moving bottom mirror. Here is the mind-bending part, and it is crucial. Both you and the astronaut have to measure the speed of light, or the speed of the photon in this case, at the exact same constant value. That is the unbreakable second rule, but you can clearly see the photon taking a longer distance traveling along those diagonals. And if speed equals distance divided by time, and the speed must stay the same, while the distance has demonstrably gotten longer, then the only possible conclusion. The only way for the universe to reconcile these facts is that the time for that journey must have gotten longer too. This means that from your perspective, the astronaut's clock is ticking slower than yours. While her clock goes tick, yours might go tick-tock, tick-tock. Time itself has slowed down for the astronaut and her spaceship relative to you. This is not a mechanical glitch, it is not an optical illusion, and it is not some trick of the eye. It is a fundamental property of reality itself. This incredible effect is called time dilation. And time dilation is not just some theoretical exercise for physicists to debate. It is real, and we see its effects every single day. Take GPS satellites, for example. They orbit the Earth at high speeds, and their onboard clocks run slightly slower than the clocks on the ground, precisely as Einstein predicted. Scientists have to constantly correct for this subtle but significant time difference. If they did not, your GPS navigation would be off by several kilometers every single day, sending you on a wild goose chase. We also see it in massive particle accelerators. Short-lived particles called muons, when sped up to near the speed of light, survive far longer than they normally should have. Why? Because from our perspective, their internal biological clocks have slowed down dramatically. The faster you move through space, the slower you move through time. This effect gets more and more dramatic, more pronounced and more profound as you get closer to that ultimate cosmic speed limit, the speed of light. But what happens if you actually get to the speed of light? Well, we will get there. But first, we need to look at the other side of this strange relativistic coin. If time can stretch and become elastic, what in the world happens to space itself? Einstein showed us that space and time are not separate entities. They are interwoven together into a single four-dimensional fabric that we call space-time. You simply cannot mess with one without profoundly affecting the other. The light clock experiment vividly showed that moving through space slows your journey through time. So it stands to reason that it has to affect your journey through space too. Let us go back to our astronaut and her spaceship. For her moving at high speeds, her time is passing more slowly than yours on the ground. But to her, everything feels completely normal. In fact, from her point of view, it is you on the ground whose clock is running fast. Remember, relativity is well relative. So, who is right? You both are. Your measurements are equally valid in your own frame of reference. This beautiful symmetry leads to another bizarre and utterly fascinating result. To keep the speed of light constant for everyone, not only does time have to dilate, but the space itself has to contract. From your point of view on the ground, an object moving at relativistic speed will appear shorter in its direction of motion. Now, this is called length contraction. Imagine our astronaut is flying a 100-meter-long spaceship. As it zips past you, you will not only see its clock ticking slowly, but if you were to measure the length of this ship, it would be less than 100 meters, perhaps 80 meters, or even 50 meters, depending on its incredible speed. The spaceship has physically shrunk, or at least from your perspective. The astronaut inside, however, would not notice a thing. To her, the spaceship is still a comfortable 100 meters long, but if she were to measure the distance between 2 points in your stationary world, she would measure that distance as being shorter. Again, this is not a visual trick, like something appearing smaller in the distance. It is a real physical contraction of space itself. The universe literally rearranges its spatial dimension from your point of view to absolutely guarantee that you will always measure the astronaut's headlight beam traveling at the speed of light. The faster something moves, the more it contracts. And just like time dilation, this effect becomes extreme, almost absurd, as you get closer to the speed of light, as the universe in the direction of travel starts to flatten almost like a pancake. So now we have two key mind-boggling results from special relativity. The faster you go, the slower time passes for you, and the shorter distances become in your direction of travel. Now, the moment of truth. What happens if we take these two incredible ideas, time dilation and length contraction, to their absolute logical limit? What happens if we try to imagine conceptually at least the perspective of light itself? We are now ready to take the final astonishing leap. Imagine you are a humble photon created in the fiery core of a star in the distant Andromeda galaxy, some 2.5 million light-years away. Your destiny, your singular purpose, is to travel across the vastness of intergalactic space and end your journey by hitting an astronaut's eye on Earth. From the astronomer's perspective, here on Earth, your journey is an epic saga that takes a staggering 2.5 million years. For 2.5 million years, you cross an incredible, almost incomprehensible distance at the constant and unyielding speed of light. But what is that journey like for you, the photon? First, let us consider time dilation. The elegant math of special relativity shows that as you get closer and closer to the speed of light, your experience of time slows down, heading inexorably towards zero. At the actual speed of light, time dilation becomes infinite, which means that for you, the photon time stops completely. The moment of your creation in that blazing Andromeda galaxy and the moment of your absorption in the astronaut's eye on Earth are not separated by 2.5 million years or even a single nanosecond. No. For you, these two events happen at the exact same instant. No time, not a single tick has passed at all. It is utterly instantaneous. And second, let us apply length contraction. The formula for length contraction shows that as you approach the speed of light, the universe in your direction of travel shrinks, getting smaller and smaller, heading towards precisely zero. At the speed of light, this contraction is absolute. The enormous 2.5 million light-years of distance between Andromeda and Earth shrinks down to absolutely nothing. From your point of view, the distance you traveled was exactly zero. So let that mind-bending idea truly sink in. From the perspective of a photon, its entire journey across the cosmos. A journey that to us takes millions of years and spans unfathomable distances is both instantaneous and covers zero distance. It is emitted and absorbed at the same place and at the same time. For light, there is no journey. There is no duration. Now, to be fair, to the brilliant physicists watching, there is a technical glitch, a small but important caveat. Strictly speaking, a photon cannot truly have a perspective or a frame of reference in the way we humans do. A reference frame is defined as a viewpoint where you are at rest. But one of the core defining rules of relativity is that light moves at the speed of light in all reference frames. So nothing, absolutely nothing, can ever be at rest with a photon. So talking about what a photon experiences is a conceptual shortcut. It is what the mathematical equations show us happens in the limit as you approach the speed of light. It is the logical, unavoidable conclusion of the fundamental rules that run our universe. This strange, timeless, and spaceless reality of a photon is not just a mathematical quirk or a philosophical curiosity. It points to a fundamental nature of space-time itself. Einstein's theory showed that while different observers can passionately disagree on how much time or how much space separates two events, they will all agree on something called the space-time interval. For any two events connected by something moving slower than light, like you walking to the office, we call the interval time-like. Cause and effect are possible. There is a clear before and an after. For two events so far apart that not even light could travel between them, we call the interval space-like. They are causally disconnected. Imagine the Cuban Missile Crisis and the birth of a star in another galaxy happening on the same Earth day. These are space-like events. One could not possibly have caused the other, but the path a photon takes is utterly special. It is called a light-like or null interval. For any path, Light takes, the space-time interval is always mathematically zero. This is the real profound physics behind the statement that for light, there is no space and no time. Its entire existence from the moment of emission to the moment of absorption traces a path of zero length on the incredible fabric of reality. We can visualize this with a light cone. Imagine a star exploding in a brilliant supernova. The light from that blast spreads out in a perfect sphere. If we graph this on a space-time diagram with time going upwards and space going across that expanding sphere of light forms a cone shape. The surface of this cone represents the path of all the photons from that explosion. It is the very boundary of causality. Anything inside the future light cone can be affected by the explosion. Anything outside it cannot. The photon itself travels along the very edge of this cone, defining the absolute limit of cause and effect. It is the ultimate messenger, weaving the cosmos together with its instantaneous connections. Yet, for the messenger itself, the message is delivered in an instant. We began this incredible journey, seeing the world through our own familiar eyes, a world of solid, unmoving distances and a steady, universal clock. But what we have discovered, thanks to the brilliant insights of Albert Einstein, is a universe far more dynamic, more elastic, and more mind-bending than we could have ever imagined. We have seen how our common-sense view of reality shatters when confronted with the universe's ultimate speed limit. We explored how space and time are not separate, but a single interwoven fabric called space-time, which warps and stretches to accommodate this cosmic rule. We have witnessed the astonishing phenomena of time dilation and length contraction, not as illusions, but as fundamental changes to the very structure of reality itself, affecting everything from GPS satellites to subatomic particles. And finally, we dared to peek into the perspective of light, finding a realm where millions of years vanish into an instant, and billions of miles shrink to nothing. For a photon, there is no journey, only an instantaneous leap from beginning to end. The philosophical implications of this are truly profound. Our human perception, limited by our sublight speeds, tells us one story of sequence and separation. But light, the very essence of how we see and understand the universe, tells another. It tells a story where everything happens at once, where distance is an arbitrary construct, and where time is but a fleeting illusion. It is the universe's ingenious and elegant mechanism for maintaining the absolute speed limit, a cosmic constant that shapes all of reality. This journey into special relativity is just the beginning. It is the foundation upon which Einstein built his even more encompassing theory of general relativity, where gravity itself is revealed as an extreme warping of space-time. It is a universe that constantly challenges our deepest assumptions, inviting us to look beyond what our eyes tell us, and to embrace a reality far stranger, far more fascinating, and infinitely more beautiful than we could have ever imagined. So what other cosmic secrets are waiting to be uncovered? If this journey into the timeless, spaceless world of light has ignited your curiosity, then please give this video a thumbs up. Share it with your fellow explorers and subscribe to the channel for more mind-bending physics. We love hearing your thoughts. So tell us in the comments below what aspect of relativity blows your mind the most. Until next time, keep exploring the wonders of our universe.